Good day to you. This is Anna Galactic on the 14th day of May 2025 from Chico, California. Over here you'll see a very simple graph. It's an interesting process to try to get out a discovery in coherent, cogent fashion. So the binary number system parameterizes the plane in a way that no physicist or mathematician has ever even surmised. We accepted René Descartes' two linear number parameterization of the plane. That has led directly to the three major tools of linear algebra here, which you're going to see over here, is a curve. It's not a straight line, although you see there is a straight line, and if you look carefully, there are two straight lines that essentially meet at zero on the far left. So what is this curve? I'll show that to you in a moment. And I'm leaving it on the screen while I complete my introduction. I always do this. It has an upside and a downside. It's like, just get to the point. We're Americans. We need immediate feedback. Come on. Instant gratification. Well, science doesn't work that way, although at certain phases it does, and that's really what we live for, is an insight, a new understanding. Oh my God, I can see how a galaxy is born or something, how two electrons do something at distance. Oh man, I feel so much better. I do want to interject here, as I often do, because it's so critical in the process of science for you, for me, for an individual. It does come down to an individual. What are we doing in science? What are we looking for? I am a guide, and so I'm just going to tell you, without too much proof, because we're trying to get into something very technical right now that's of immense value. You have to analyze yourself daily. It doesn't have to be every day, but cyclically, regularly, periodically, you have to review yourself. It's just silent, you're just talking to yourself. Why am I doing this? I could be in a band, I could be looking at videos, I could be looking at dancing girls, doing something else in life. Why am I studying science? Here's the reason, and I'm just going to tell you because I'm your guide. And if you don't like your guide, you always get rid of your guide. You can certainly get rid of me. It's real easy. Click. No more guide because you don't trust him. Well, I hope you do trust me, so I'm going to give you some trustworthy information. The reason we are studying science, and now you know this is individual, so it's personal. So I can't tell you why you're doing science. You're looking for something. What are you looking for? You're looking for orientation. What does the universe say to you that might help you in life? Well, I know the answer, but you don't. And I can't tell you the answer because even if you believed me, you wouldn't actually see it. You would just go, okay, I believe you because I trust you. It's not helping you. The same thing is true in religion. It's completely individual because this problem you're trying to solve is your own. The universe wants to help you, or it wouldn't have made you. That can be rigorously, logically proved. I have, so that's why I want you to trust me in our discussion of this curve. So to recap, yesterday in the previous combined two lectures, which ran, I'm not sure how long, but it was over an hour, which I don't normally like to do, but I always do because I can't help it. Science takes some time to get across. And you do have to participate, but if you go into a university and start stacking up the calculus books, I certainly feel sorry for you. I'm dead serious on that. You're just trying to make a living, so, I mean, there's no sense of shame or guilt. It's just you're wasting your fucking time. It's just very, very inefficiently being allocated to a 4-year program in a university where you're going to have to use calculus, complex numbers, and sine, cosine. Well, those three tools for linear algebra were invented because linear algebra doesn't work. It simply doesn't. But it's superpositional. We know it does. And in fact, the binary number system is a subset of the linear number system. So that's proof enough that it works. What I discovered is the binary number system is not linear. It can be treated as if it were linear because you need one component numbers for computation. but the binary number system is a two-component number system. This number system has a name, but in fact, we named it. It is, in fact, the binary number system. But that is, in fact, a two-component number system. And we went over that. If you don't understand what I just said, you will have to watch yesterday's video, where I perfectly explained it for the first time in 3 years. And I believe I'm accurate enough in saying that, which is a big plume in my cap, but it only affects me unless I can communicate it to you. So that's my goal. So now we're dealing with a binary number system, and what does that have to do with this? So now I have to switch tacks, and it's going to take some time, but not much time. It's well spent time to dovetail these two things together. That is the binary number system and this curve. What is that curve? Without telling you what it is, I'm going to describe what it says it is. And then I'm going to show you what the two lines mean. Okay, and this will home in on our binary number system, which is the basis of all computational science. It does produce the image you're seeing on the screen now. That is directly from a binary number system, which is not all the linear numbers. Be very careful when you say the binary number system. That's not all numbers. It's only numbers that can be represented in a machine. All right. That's very specific, and it's very well known, so none of this is theoretic. Now, the curve you see, I want you to just look at that curve and kind of defocus and try to figure out, just by looking at it, what it describes. And I'll be explaining this in extraordinary detail so you see every single aspect of this curve. There's a whole list of very interesting insights that come from this curve. Normally, at least my instinct would be to just tell you what it means right away, but I'm not going to do that this time. You're going to figure out what it means from my description, and then I'll confirm or correct, as the case may be, just what actually this curve does purport to describe. All right. On a 2D projection, which this is, there are two aspects, the horizontal and the vertical. The horizontal, in Ruger Bošković's day, was called the abscissa. That's the horizontal metricized line. And you'll see at the bottom, there is this line that begins at 0 on the far left and is marked off in femtometers, which is a linear spatial separation metric. It's been metricized to an index of 1 femtometer. Now, this is not in binary because you see that it goes from 0 to 0.5 to 1.0 to 1.5 to 2 to 2.5. So it's measured in half femtometers. But that's just the hatch marks. What is the actual metric depends on the smallest measurable linear spatial separation. And what is that? It doesn't say. You could say, though, that it's 1. And that's artificial. But we are going to say it. We're going to say that this is measured 1, 2, 3. With divisions in between if you choose. And that's the normal way that a mathematician looks at the line, is that it's infinitely divisible potentially. But that leads to a paradox that leads to the Planck length, because the Planck length is the lowest physical index of the line. And that is defined as 1/2 of one wavelength. You can look that up. There are several definitions of a Planck unit. For the line, it would be the Planck length, because the metric is distance, which is identical with length. So, that's the horizontal line, the abscissa. We call it the x-axis. It shouldn't be called an axis here, because this is a projection, often called a graph, more abstractly called a diagram. But geometrically, it's a projection. It's a projection down from some other space to flat space. So this is a flattened diagram. What is it flattened from? We'll get to that. You may have already guessed that it's spherical space, but I am hesitant to even give that away because I want you to figure this out. That is to stretch your mind, to see if you can figure out what this is a graph of. So we've talked about 1/2 of the two-aspect ratio. It's actually a ratio between two linear numbers, the way it's depicted. So the abscissa is the horizontal line, using Ruger's language, which was the lingua. It's essentially Latin, yes. So what is the y-axis? That would be called the ordinate, which invariably I would get backwards trying to learn that, so I just gave up. I just am dyslexic with east, west, left, right is just strange, plus, minus, and we're getting to that. I made a big mistake explaining this about a year ago. When I got the valence backwards, it actually led to a discovery, though. What is the vertical aspect? What's the metric? If you turn your head sideways, you might be able to read that. I'm just going to tell you it's force. So this is the ratio of what is labeled range to force. Range to force. Well, what is range? Linear spatial separation. It's distance. So that's the range in femtometers. It's called range because of what it's depicting. Range refers to the distance relationship between two objects. So what objects? Well, we're getting there. I want you to guess. But you may already know. But I hope this helps anyway, because this is a synthetic approach. So force is indicated on this ordinate. So there are two aspects, horizontal and vertical. Horizontal is space. It's measuring space. And that's ambiguous. I have not completed my sentence. I was very, very sloppy there. But it's still true. It's just, it's not true enough to be accurate. It's linear. Linear. Spatial separation. LSS. I very commonly abbreviate that in my writings, LSS, because otherwise I'm writing out linear spatial separation. That takes too much time. LSS. Chick, chick, chick. It's a notational convention that I have adopted for myself. Now, force, what is that? Well, we'll talk about what that is. You may, depending on your immersion into physics or mechanics, you may have a fairly accurate idea of what is force. Your scientists do not. So be cautious in being self-assured about your conceptualization of force. I'll show you what it actually is, because this diagram shows you what it is. So force, the metric for the force is the fourth power of newtons. You would have to know what the international unit is for the newton, which is quite a study. So I'm just going to tell you it's the unit of force, which has been given the name the newton, like the inch or the mole. So this is the relationship between spatial separation on the line, linear spatial separation, distance. It's the relationship between distance. I'm going to change that to what this actually is showing, more accurate word, proximity. Proximity. That's relative distance, independent of any motion. It's the actual measurable, on a line, separation in space. It's the separation in space measured on a line between two particles. I'm giving that away so that you have a more clear insight into what is still somewhat mysterious, I hope. Because what is the relationship between distance and force? Well, that's what the blue line shows. So let's talk about the blue line, but before we do, just let's summarize that. The blue line shows the relationship between distance and force between two particles. Now, we must be more specific because there are several more aspects to this graph that just simply need to be described. First you describe, then you explain, then you prove. That's the order. So it does begin with a sort of a Gedanken experiment. So let's just look at this. It certainly is an intriguing curve. You have to admit, it looks like there are two curves, and now I'm going to attempt to show that. If I don't have a pointer, and I'm sorry, it's just my technology is not advanced. You can think of the line as curving downward, reaching a nadir, a lowest point, and then abruptly, relatively abruptly, changing direction from going curving downward to curving upward. So there are two curves depicted here. And they have a general relationship you may be able to see, but let me expand on what you might already be seeing, the relationship between these two curves. This curve that goes down is one curve. And as it goes down, the downward tendency has to do with a change in force. Okay? Is the force going down? Yes. And the reason we can say that is because over on this side, the hatch marks show the metric of force, which is centered at 0. Right here at this level, I should point this way, that 0 that you see on the ordinate, on what we would call the y aspect, that 0 is the center of the force metric. So at going up, it's more force. And going down, it's less force. And now you have to identify what force. What force? You're not saying what the force is. Right? So this is an incompletely annotated diagram. It doesn't have enough information. However, this is taken from Wikipedia, and in Wikipedia it has a caption that explains most of what I just said. So I'm just going to recap what Wikipedia says about this curve. So the curve going down denotes less and less force of some kind as the distance closes. This is relative distance, but we tend to think of closing distance as relative velocity. So you could think of this as depicting the flight of one particle toward another. Or you can look at it statically. Nothing is moving, but there's a distance between the two particles. Without respect to velocity, you can look at this graph, measure the distance from 0 on the x-axis, and then read down or up the amount of force at that distance. So this shows the amount of force at some distance between two particles. I know this is tedious, but if you get this, you're going to be ahead of your physicists and your mathematicians. So you have to trust me to trust that statement, and now I'm going to prove it. There are several ways to begin to explain what this is, and I'm pausing here to recollect the method that I wish to employ to reveal to you the deepest secrets of the universe that are displayed here. I am not sure how long this lecture will run. I have a barely sufficient amount of water to get me through this. So if you suffer at any time from tedium or confusion, you are simply sharing what I experience on your behalf, because I know how difficult this is to see. Your physicists cannot see what I'm about to show you, but the rigorous proof will underpin the accuracy of what I'm about to tell you, which is game-changing. So I'm being a little bit dramatic because at this juncture in my life as a scientist, I have completed over 960 videos in under 3 years to be able to tell you just what I'm about to tell you. So this is the relationship between two fundamental particles. The first man to draw this curve lived 250 years ago, and his work is only now, just within the past 2 decades, being recovered, and I am at the head of the list of men recovering the information that was revealed right after Newton died, right after Leibniz died. They died within a decade of each other in the first quarter of the 18th century, at which time Ruđer Bošković was in his teens. He is a very well-respected astronomer, the head of the Brera Observatory, which is still operative in Milan, that was run by Ruđer Josip Bošković of Croatia, the greatest scientist of all time. And he completed what Newton could not complete. He completed what Leibniz could not complete. And he was the only active scientist in Europe after those two men died. There weren't any others. He inherited their robe, I'll just put it that way, and he got the solution to the construction of the atom, which was not discovered officially for another century, actually more. So this is the man who discovered the Bohr atom geometry. And this curve is the Bošković curve. It's not labeled as such in Wikipedia because none of this is known officially. Wikipedia knows nothing of what I'm about to tell you, that this is the Bošković force curve, but it's only one part of it. The Bošković force curve is actually a multiple curve, and it has humps. This does not have a hump. It has one inverted hump. There's nothing above the line, except you see there's one segment that shoots up above the line. The rest of the line is below the line. So there are 2 lines here, and I'm being ambiguous. One of the lines is this line. That is the space line. That is the space line. Where is space in this projection? Where and only where is space in this projection? It's the horizontal line. That is space. Now, is space constrained to a line? We would ordinarily say no. Space we ordinarily conceive as spherical. And in fact, this diagram is embedded in spherical space. It would have to be because particles are oriented to a position in spherical space. So that horizontal line is where the particles are, because the particles are in space. And so both particles are on that line. One of the particles is at the 0, 0, and it is a double zero as we discussed yesterday. It's vertical 0 and it's horizontal 0 simultaneously. So this is simultaneity at 0. Nobody knows this directly the way I do, because I can prove what I say. So one of the particles is at 0, which is a contradiction, because a particle has a property that it's actually there, whereas the 0 is not there. It's virtually there because it's in a geometric space, which defines that point as 0 vertical, 0 horizontal. So it's a double 0. Both of those are Euclidean conceptual points, but they're overlaid. They're superpositional zeros. So that's a lot of information. I hope that doesn't baffle you. The reason it might is I haven't told you why that's important. The reason it's important is because it's 0 force at the same time as 0 position, which the 0 position defines position. 0 force defines nothing, except relative to force, which is absent there. There's no force. So there's no force at that position. That's 0, 0. No force at that position. 0, 0. No force. So what is the square space? The square space is force. It's not space. That's extremely important to realize. The only space here is that horizontal line. That's space. So it is a projection down from a sphere to a line, which is a jump of at least 2 dimensions depending on how you measure dimensionality. But it's definitely, you're losing information when you project downward. Just as with the light cone diagram of 4D time-space or space-time, that's a projection down of 2 linear dimensions, from 4 to 3, which still can't be represented on a flat sheet, to 2. So it's a 2D graph of a 4D system. This is a 2D graph of a 2D system. And that is not quite accurate. It's a 2D graph of a spherical system that's been projected down to 2D. Space in this diagram is 1D. So there's no space except for 1D space. That line is space. It's spatial separation on a line. So I keep repeating that because of what comes next. You have to bear a lot of things in mind in order to achieve a synthetic insight, which is understanding. So I'm going to cause you to understand this. And that's quite an intimate transaction. You do have to trust me somehow. Well, that's why we have the scientific method of proof. So I'm going to explain it, and then I'm going to prove it. All right? First, I have to describe it. You have to know what this shows before it can be explained, basically how it's showing what it's showing. All right. So space is only on the line. The rest of the flat space is force, which above the line is positive force. That is above the space line. Above the space line is positive force. Below the space line is negative force. This, according to the Wikipedia article on nuclear force, which you can look up and look at this diagram yourself, it's in that article. The nuclear force. What is that? As stated, even by Wikipedia, and admittedly in the first paragraph of that article, it is admitted that the term nuclear force is completely ambiguous. You still have not identified what force you're talking about, in at least 2 respects. First of all, what do you mean by nuclear? And second of all, what do you mean by force? Because forces come in different context. So this is the relationship between 2 protons, according to the Wikipedia article, and that, of course, is their basis, so I'm not questioning that in any way. This is a cutting-edge diagram. This is where our knowledge of the universe stops. Because in here you're going to find the quantum, and you're also going to find 2 infinities. So again, I'm giving it away, but I have to give this away progressively so you maintain continuity with my thought process, which is correct. And you now need to match your thought process with what I'm able to reveal to you. All right. This does have a proof. So I'm asking you to trust me on that basis. Sorry, my phone just rang, but I've set it to just beep once. Turn your cell phones off. That's correct. I need some water. I'm going to put this on pause. This is a hazardous thing for an asthmatic to do, but I find this to be medicinal. I'm allowing you to see this so you know this stuff is harmless. Although it's not harmless to me, I'm asthmatic. Okay. Again, pardon my asthma, but I want you to see this whole process. I'm not ashamed of my humanity. Yes, I'm weak. But I'll tell you what. This is strength itself. I'm going to impart something to you that I probably should be charging $1,000 a head to listen to this. I do this for free because I have my reward, mate. You don't need to worry about me, life or death. I made it. You're going to make it too if I have my way. But that is up to you because only you know your personal equation. Nobody can solve that for you. But it does help to have a guide. I recommend the universe. That's called science. It's called using your rational, logical on-board system the way it's supposed to be used, according to the way the universe blueprinted you. And if you don't have that direct perception yet, get it now. The universe programmed you to understand it. So there is definitely a higher order consciousness. You will deal with that or you won't make it. Okay? I'm just telling you as your guide. This is the human side. Now, to return to this very simple looking diagram, this is the relationship between two protons in two aspects simultaneously. So this is a very interestingly constructed curve. As two protons with relative velocity approach each other, this graph shows you the force relationship between them. At this distance, if it were 2 femtometers, you can read this graph over to the 2 femtometer mark and then look up, and where that vertical line that you draw from 2 up through the blue line, where it touches the blue line is the exact amount of force between the two protons. Now, using this diagram directly to compute that, if you have these two protons that are 2 femtometers apart, the force relationship existing between them is about 1/2 of that metric unit. But it's negative. So it's negative 0.5 force. So what does that mean? It depends on the interpretation of the force. Because what's above the line is the opposite force of what's below the line. What is that force? It's attraction-repulsion. Attraction-repulsion is the force. You can see it has 2 words in the name. It's most often abbreviated to one or the other, but you can see the disadvantage in doing so. If you say it's measuring attraction, by convention, we interpret that when we hear it or we say it to ourselves, that would be positive force, would be attraction. If this is depicting the attractive force, then the relationship between these two protons is not positive, it's not attraction. So that would be repulsion, because where the ordinate meets the curved line, that registers as a number in force, but it's a negative force because it's below the space line. So it's a negative attractive repulsive force. Well, which one is which? You have to say so, you have to state so, and I've gotten this backwards several times. I just want to tell an anecdote so you know how critical is this ridiculously simple distinction. It is so necessary to get that perfectly accurate in your mind because it's so easy to get this backwards because of the nature of the force relationship. Now that's putting out a lot of very abstract, ambiguous information. That's because that's where physics is at. And I'm going to now lead you beyond what physics knows. So that's to get you interested. I hope you are. So we could say that at a range of 2 femtometers, these two protons have a net repulsive force relationship. Well, what does that mean? It means they repel. Correct? So what should happen? If you start action, in an experiment, for instance, to see what they do, that's how we got this information, was to see how 2 protons behave at close range. How do they behave? They repel. And that's a charge relationship, as we interpret it in electrodynamics. You may at some point, perhaps even now, put this on pause and look this article up in Wikipedia and see what they say. and see if that matches what I just told you. I'm going to put this on pause and I'm going to actually bring that screen up. I want you to know what Wikipedia says about their own diagram so I don't get it backwards again. I did so in my most popular video, which got 1,712 views in 3 days and then stopped. It's now at about 1,750, but that's a year later. So this was massively watched, the video to which I refer. I'm now going to show you the Wikipedia article. I will return in a split second. All right, here is our article, which I'm just going to read swiftly. The nuclear force is a force that acts between protons, most commonly observed between protons. Protons are affected by the nuclear force. Protons have a charge. They experience that charge that tends to push them apart. That's the electrostatic force between 2 positively charged ions. They are pushed apart. That's repulsive force. But at short range, the attractive nuclear force is strong enough to overcome the electrostatic force. All right. All right, this is the Wikipedia article itself. You'll see the inset. That is the diagram we have been studying. I'm just going to read this. Force between 2 protons as a function of distance. The attractive force is negative. Okay. Now, you may have already intuited why it says the opposite of what I just said. And this is going to lead to a major insight, actually a series of insights that I've had that I am going to attempt to duplicate in your mind so you see it too. And this is going to be instructive, I certainly hope. All right. So let's return to our other diagram. Now here we are back at that same diagram from Wikipedia, where I just got done telling you basically what you would assume if you had no other information about force, is that below the spaceline is repulsive force, because it's negative. It's the opposite of attractive, but this is not set up that way. It's set up just the opposite, because what you're seeing here is not the electrostatic force relationship, which, if it were, I accurately described the charge relationship between two protons, such that at the range of about 1 femtometer and greater, this goes on the graph from the nadir, the lowest point, curving upwards to the right, that is all below the line. It's below the space line, which normally, I would say by conventional interpretation, would normally be interpreted as the negative of attractive force, because this is proximity. So this can be interpreted in two opposite ways. If you see this as describing the electrostatic force, then what is below the spaceline is repulsive electrostatic force. But that's not what Wikipedia is showing. It's showing a closer range. And it said so in the article, which is one reason I wanted to read it to you, is because the strong force is the opposite in valence in force relation. The electrostatic force between two same charged particles, two plus charged particles as we conceive the protons, would repel. They would repel. And therefore this diagram would be showing that they have repulsive force all the way on a decreasing separation. The repulsive force goes up until it reaches about 1 femtometer, at which time it starts to decline rapidly. And at about the 0.8 femtometer mark, where the blue line skyrockets and crosses the space line, where it crosses, there's a zero force relationship. There's no force between the two particles. But if the proximity decreases now, or they get closer than about 0.8, then the force relationship, you can see, will suddenly invert to attractive force. And that would be the electrostatic binding range, so that the two protons would come into equilibrium and no longer be either repelling or attracting. At the 0.8, where the blue force line crosses the space line, that means that the two protons are separated now by a distance of 0.8 femtometers. At that range, if there's no relative velocity, they'll just stay there. It's a tipping point. A tipping point. Highly unstable. But contradictorily, it's also the most stable range, because at that exact range, they don't repel or attract. They just would sit there. Obviously, that couldn't last very long, because the slightest change in proximity would entail, if they get just a little bit further apart, they will then drift apart forever. They'll drift apart forever. And I'll show that to you. That's an aspect of this graph. They will drift apart forever. Under one interpretation, I would have to put it, because forever, I don't even know what to think about that. It's imaginary. Yes, that's right, it's imaginary. But if they get even the slightest bit, that is, a quantum of space separation closer, then we can see from the aspect of the ordinate direction, the aspect of the force direction, which would now be attractive, they accelerate toward each other. But they accelerate toward each other without the distance closing very much. So they accelerate as they slow down, and that's a direct contradiction. The two particles accelerate in velocity as they are unable to achieve infinite velocity or infinitesimal spatial separation. They would collide. They don't collide. But as they approach now, their relative velocity is going to infinity as they slow down in space. So velocity is not a purely spatial relationship. It's very interesting, isn't it? That blue line is not going through space. It's indicating an increase to infinite force, which in this case would be attractive force if it's the electrostatic force. But it's not the electrostatic force, which is actually further out here, is where they would have the electrostatic range of two protons. This is not proton-electron, which is another confusing aspect and I don't want to introduce that now for this reason. Because the Bošković force curve shows the relationship between two any particles. And that's quite interesting, that his force curve describes both the electron-proton relationship on a series of curves which accurately describe the shells of the electrons. But this is a single curve in comparison with the electron-proton relationship, which is a multiple curve, which Ruger drew accurately enough. It's an algebraic curve that describes the Bohr atom shell system. So that's remarkable. This doesn't have those humps. It's not proton-electron. It's proton-proton, but now to really make it interesting, there are two different protonic force relations depending on the range. The electrostatic force is not on this graph. So I have to change to what Wikipedia says, because what I described to you was the natural relation. That is the first relation, the primary relation in terms of outwardness, that as two protons relate, they don't. They can come toward each other if they have relative velocity, but it'll slow down. And if the relative velocity is not sufficient to get past the nadir, going like that, then it will stop. They'll stop. And then they'll start to drift apart. That's what this graph shows. So this does have to do with relative velocity if you interpret it that way, but you can also interpret it statically, which is a third confusing factor. So now we have 3 layers of confusion. And this is enough to put off most people, because they simply can't juggle such concepts. And I'm one of those people. So this took a long time for me to get past this hump. Just kind of like two protons trying to bind. And that is, in fact, what this graph depicts, is the binding range of two protons, not due to electrostatic repulsion attraction. Instead, it's due to the strong force. And this is the graph of the strong force in its original and correct interpretation. It has nothing to do with chromodynamics. We're not into the quark system yet. Those are subatomic particles. They're actually they're subparticle particles. They're not really particles. They're subparticles. And so we're not talking about quarks or anything in the standard model, because those aren't natural particles. Only the proton is a natural particle. And by extrapolation, we can demonstrate that the electron has a specific geometric relationship to the proton, wherein it is sometimes a particle, but not when it's near the proton. The electron is not a particle, it's a standing wave, and that's the wave-particle duality. So we're getting into quantum mechanics, of course. This is the curve that quantum mechanics is trying to understand and so far has not. I'll show you how you can directly understand what your physicists and mathematicians will never understand. There is a loop, there's a way to understand it, but alas for the scientific mathematical physics community, they would have to listen to me now, and that simply cannot be done. So anti-science rules now. That makes no difference to laymen. We don't have to conform to an anti-scientific community. That's exactly what you don't want to do, is do what your physicists and mathematicians do, which is what? Now, it can be defined what they're not doing right. They're not listening to me. Well, 3 years ago, they would have been off the hook because I had not made the discoveries that explain this. So here is what the strong force says. It's the same curve as the electrostatic curve. Now, you don't have to accept that. I'm just saying that's what I know. Whether or not you accept that or not, it really is simply an inversion of the force valence that would describe the strong force as opposed to the electrostatic force. For the electrostatic force, the range between the two protons going into a limit is repulsive. In the strong force, it's attractive. So once the two protons they have relative velocity to overcome the electrostatic force. Here's what happens next. Now they're actually doing what? What happens if two protons have relative velocity sufficient to overcome their electrostatic force? Well, then they would accelerate toward each other based on a force inversion. They're no longer repelling, but it's getting less and less distance. Once it infinitesimally crosses that Lagrangian point, and it is a spherical Lagrangian sphere, if it gets through the sphere, so they're now closer, then the Lagrangian, which is the zero force on the spaceline, then they accelerate because it's inverted. They start to accelerate, but they don't have room to accelerate. Well, what do? Can you figure out what the two protons must do? Because if they actually continued to accelerate toward each other and overcame space, they would collide. And the blue line would go to zero because they would intersect. That does not happen. What happens instead? Well, if they can't collide, but they're accelerating, they have to go perpendicular to accelerate, and that's not through space. So the particle in this case is shown leaving space. This is the departure of one proton from space into another dimension, but it's not a linear dimension. That's what I can prove to you now. So this is very interesting, that space has an imaginary dimension. And that is true. I proved that. And that is a major insight. And it changes mathematics. And it changes the geometry of the universe that we can now perceive directly. The true force relationship that governs the universe at all scales. So, this is where it begins. It has to begin at the quantum, otherwise you can't measure it. You can't measure this without the quantum. You're looking at the quantum. And if you can figure out where in this diagram is the quantum, you have the answer to everything in the quantum paradox, including the collapse of the wave function and the rationality of entanglement. And you'll understand everything about physics from this. So this is revolutionary. Game-changing completely. So you can see why I might show some emotional ellipticity in my attitude towards science in general, which now needs to listen to me. And that sounds megalomaniac. I sound like a troll. I'm an outsider trying to get in. There are millions of creeps like me. So I am in that group by default. A nut job. I don't like that because that's what I've been trying to get away from all my life. And now I have to face the music. I'm going to make this so easy for you that it's ridiculous. So I ask in all humility, pay attention to what I say now. I've been practicing for 3 years continuously to do this. This is the strong force. So as one proton comes in towards the other proton, you can see that it's accelerating. It's not repulsive. It's not electrostatic. This is the opposite valence force relationship. The two protons are now accelerating toward each other. It's relative. It's mutual. It's a relationship. It's not one having velocity and the other not having velocity. The whole basis of relativity is that velocity is relative. And that is so obvious it really shouldn't be a problem, but it has been, because it's mathematically and geometrically difficult. But when you state it plainly, it's obviously true. So relativity pertains to velocity, and that's how you can understand it. That when two particles are coming toward each other and you have no frame of reference, they're both moving. You could say that in several ways, but its relative velocity is the right way to say it, and Albert proved it, so we got that. So we have relative velocity depicted here, but it's based on the force, which controls the velocity. It regulates the velocity according to distance. It'll either slow down the velocity or it will accelerate the velocity. Deceleration or acceleration is depicted here. One is above the line, one is below the line. Which the fuck is which? Again, in my most popular lecture, I got this backward. I must have said it 5 times backward. Even though I had looked up the article, and at some point I knew, I still said this as if it were the electrostatic relationship, which once again is off of this graph. They've penetrated the electrostatic repulsive range, and now they're accelerating toward each other. Here's what happens next. After the repulsive range is overcome, and now they're... Okay, this graph shows right after the electrostatic. It's not exact, though, because this is strictly limited to the nuclear force. So what's off the edge going this way is not defined, because we know there's another hump that was already overcome to get here, and so this asymptosis is illusory. So this graph is wrong. And that's what caused me my dyslexic reaction. It's still my fault, but I can definitely point the finger at Wikipedia and say, you've got to change that motherfucking graph, because it's causing me some problems, and I have the right answer. So change your diagram so that the right side of this diagram is not an asymptotic relationship between space and force, because there's something on the other side of this terminating line on the right. Has a shape which denies the asymptotic relation. That is not an asymptotic curve there. But you could isolate it and then just have some indication that the asymptosis shown going horizontally this way is not true. There is not that relationship there. It does not go off to infinity. So that's... I hope that is confusing, but now I'm going to deconvolve it, so if there was a moment of confusion that perhaps is still persisting, it'll be gone in a moment. The two protons have overcome their repulsive force and are now accelerating toward each other. As they do, this one coming in on the spaceline is accelerating until it reaches the bottom of the curve, in which case they're at extreme close range. Quantum close range. They're as close as they can get without something happening. That's called collision. So they're on a collision course and they're accelerating. And the dip in the curve shows that. That's acceleration. Now they're extremely close, but the distance between them is now measured in fractions of a femtometer, so the scale changes, really. And now they're so close, they're almost touching, you could say, but now they're not accelerating. There's a relative deceleration such that there's still velocity, but the acceleration is no longer increasing. The acceleration is slowing. And when they reach the 0.8 femtometer Lagrangian, there is no force. But if there is still relative velocity, the graph shows what happens if they continue at relativistic closing speed, that the repulsive force goes to infinity. And that means they stop. Not exactly, though. If there's sufficient velocity, one of the particles goes out of space into another non-spatial dimension. So you're seeing one proton and another proton at relative velocity overcoming the strong force, which is attracting them, and they're overcoming the attraction. It's another change of valence. The opposite of the electrostatic force inversion, this is inverting it again. So that now, instead of accelerating, the particle is over here. I don't have a pointer. God damn it! Sorry. The spatial separation that is still decreasing entails an asymptotic shoot to force infinity, which is impossible. So there is definitely a change of dimension, because they can't do what they're doing. And they don't. And this graph shows that they don't. There's no violation of physics here. They get to this range and accelerate until they get to 0.8, in which case, if there's more acceleration, you get a hadron collision. In a hadron collider, it can be forced. And that's a good pun. And the way that's done is by artificially investing one proton with energy by velocity, which requires a magnetic attachment to the proton. So it's no longer just a proton. It's a proton at subluminal speed, heading for another proton. This is a cloud of protons, because these things don't normally collide. Protons don't collide, ever. They don't collide. But if you force it, using your knowledge of electro-force relationship, you can give the proton artificial energy. And that is not energy. Although you could say it is. It is and it isn't. Because of what happens when the two protons are forced, so that they actually defy this curve. Because they go to zero. Do they? This diagram proves that they can't. It doesn't make any difference how much energy you give the protons. You can give them both that velocity and collide them. It turns out that that's redundant. That's the two-car collision problem, which is quite counterintuitive. But you only have to accelerate one. If you accelerate the other, it's just, you're not adding. You only have to accelerate one particle. And with a huge amount of energy, and it is a huge amount of energy injection to get one proton to go that fast, so that when it comes into the cloud of protons, which are relatively static, you would have to say, it can hit one of the protons. But this curve shows that they don't collide. And that's driving the particle physicists literally stark, staring, lunatic, mad, crazy. They're psychotic. They don't know what to do with the information that comes out of that collision. They've never been able to figure it out, with one exception. A man named Gelman, Gelman is how he misspells his own fucking name. Can you believe that? A man of his stature who got closer. He's the one who discovered what is now called the quark system, the basis of chromodynamics. All it is a very interesting piece of mathematics that helps describe this curve and hadron collision. Hadron means proton, and that's all it means. Whatever else they say is relatively meaningless, because there's only one space particle, and I'll show that to you. The proton is a space particle. You know why? It makes a position. Otherwise, we couldn't measure linear separation, because linear separation, as Euclid proved so well, is the separation between 2 points, which are positions in space. But this doesn't show just position in space. It shows position in counter space. And that's what happened. That explains this. So let me show you how this is explained with another space that you can't see. The proton sees it. The proton sees it perfectly. That's called geometry. We can see what the proton does. In natural space, not Hadron Collider space underneath the soil of Switzerland, or anywhere, Chicago, it doesn't matter. That does not occur in nature. It just doesn't. Protons do not collide the way they're being forced to collide. You could say they could. They probably do. Maybe in the center of the sun, they come together so fast that they repeat the Hadron Collider experiments. That might explain a lot about what we mathematically seem to perceive in terms of funny particles coming out of stars. It may be because there are hadron collisions going on in the star. Highly artificial. Nature knows exactly what to do. It just dissolves back into the ionic system as energy and is reconstituted. There's no loss. There's no entropy. There's no such thing as entropy. And I'll show that to you, because entropy is a hugely misleading topic. And if you study entropy, you'll be confused. Or you won't understand it correctly, because it's confusing. This is not. But it's been confusing until I saw how to see it geometrically. And this goes back to the binary number system, which we just talked about yesterday. And it will tie all of that together into a number system that describes the quantum curve. So that's a lot, and I'm exhausted. So I'm sorry, but I am suffering from huge allergy attack, which is asthmatically induced because I breathed 3 hours of deadly toxic campfire smoke as I attempted to get out of the burning city. And my tires almost melted before I got out, and I was one of the last to get out. Although I was the first to see the fire, because I was up all night doing mathematics, and I went out on my porch, looked at the beautiful eastern horizon, because I was on Pence Ridge, where the fire did the most damage. And it got my home and my life's work and all that. But I'm so tired right now, I have to get water. My stomach is growling like a bear that just woke up. I said this yesterday. From hibernation, I'm so hungry, thirsty, tired, angry, lonely, whatever they say in the 12 steps. By the way, just one parting comment for those of you who may be alcoholics, which is a genetic feature. I wouldn't say it's a disorder. if you're alcoholic, and I've known several alcoholics, they're just like you and I. They're human, but they have a genetic feature whereby if they start drinking alcohol, their body reacts differently than just a common drunk or a common problem drinker, which I could certainly be classified as. I fell in the creek just 3 weeks ago and could have died. I was so inebriated I fell off the cliff where I was attempting to perform a skit and sing or whatever I was doing drunk. And I fell in the creek and ripped open my elbow, which is healing properly. I don't even feel it, but my God. Well, that's a problem drinker. I don't cause anyone else any problems, but you can see I can cause myself some problems, but I'm not an alcoholic. If you are an alcoholic, they say go to 12-step meetings. I did for a year just because I liked it. I liked listening to these unbelievably horrendous stories of how people can ruin their lives. Well, if you're an alcoholic, you will ruin your life. But I don't counsel people to resist it. If nature is telling you to drink yourself to death, I don't argue with nature. My wife was an alcoholic, and she found out that she was, harshly, as all alcoholics must, and then she stopped drinking, and that's the only way to save your life. But I don't counsel people to stop drinking. It's just be aware of your condition. If you want or need to drink yourself to death, I'm not saying you shouldn't. I'm just saying make sure you isolate yourself. That's really difficult with an alcoholic because their bodies are so constituted that they can drink orders more alcohol, orders more of alcohol, mass quantities of alcohol that would kill me instantly. The amount that I've seen alcoholics drink will not kill them, but it puts them into a state that even though you are conscientious and isolating yourself so you won't hurt anyone else, you'll break out. You'll be delirious, and you'll kill yourself and someone else. Most likely because you don't know what you're doing. So it is a dangerous disorder. I would have to call it a disorder in that context, but it doesn't necessarily have to be. For instance, if you're in a jail cell and you can't get out, and your life is just unlivable, say you have a life term and you can't stand it, you're getting butt fucked. It is too much. You just want to die. Well, you have to do something, get some money from the outside and bribe some of the guards. This is done all the time. You get some heroin, get some barbiturates, but really what you want is a big old quart of just grain alcohol, 120 proof if you can stand it. Just water it down and gulp to gulp to gulp. You'll die, but you won't hurt anyone else, unless you have a cellmate, in which case he'll probably help you die, because you'll be a drunk. But alcoholism is not a sin. It's not really a disease, but it can be a severe disorder, and always is. So I'm just going to give you a recommendation. 12-step meetings can help. And there are reasons for that which are quite mysterious and interesting, but practical and will save your life. I've known many men that have saved their lives by going to 12-step meetings, because you have a genetic disorder. It's not your fault, but it will become increasingly your fault if you don't do something about it. You must not drink ever again. And then you'll live normally. And you'll be extremely unhappy for a long time, because you'll want it. Because everyone else is drinking, why can't you? Because you don't have any legs, that's why you can't walk. And that's what you'll learn in 12-step. A lot of good stories, although you got to have a pretty healthy stomach to hear some of these stories. My God, you did that to her again after how she tried to help you, and my God, look at her now. Oh, you hate these fuckers. But they're just, it's very strange, this thing about morality and genetics. But whatever the case, I hope you got something out of this. We're certainly not done. This is just the beginning. I'll show you the two asymptotes of infinity. We'll go to the proton-electron system. I'll show you the inner structure of the proton that the physicists don't know, that I discovered because of my dyslexia. And keep looking up. It's a beautiful full moon that's now waning. It's the opposite of waxing, I told you. Yeah, it is waning. It's past full, but it's still full. Because everything is continuous and quantized. We'll be right back. This is Intergalactic, bringing you the secrets of the universe now. Thank you so much for tuning in. It means so much to me. And I'm going to eat and rest for a while.